Let's get going. Hopefully, a few others will join in shortly. But just for the agenda portion, I had requested Steve to kind of share his experience with Catalyst. And Catalyst is one of the platforms that was posted in some of the Kaggle discussion groups that it's a very useful platform that many people have been using to participate in Kaggle competition. So I thought since Steve has used it to make several submissions on this Sevastell Steel Challenge, him just taking us through an example of what he has done on the platform would be good exposure for everyone trying to or becoming familiar with the platform. And after Steve is done, we've been discussing two papers we have completed discussions on. One is PSPNet and the other are versions of the Deep Lab leading up to the Deep Lab v3 Plus version, which is the most recent version. And Rekel said he had an implementation of PSPNet and possibly Deep Lab v3 Plus also if we have the time. If not, next week we'll continue with Deep Lab v3 Plus, and once Rekel is done with that, we'll switch to discussing HRNet, which is kind of like the final paper for image segmentation that's relevant to this competition. So with that, take it away, Steve. We can see your what is it? The screen with ML Comp Catalyst on it. Go for it.
Yeah, you can see it okay. Yeah, so in this competition, like a lot of the people who were at the top of the leaderboard, they were all using Catalyst. I think part of the reason for that was this submission. This guy here, I think he like works in the Catalyst team, and so like he put this submission on, and like it's got like a very high score. And so like obviously, as happens in Kaggle, I think a lot of people just copied his kernel and then sort of took his models and expanded on it. So I think that's partially why it's like so popular in the steel competition. Within this notebook, he's got this other thing, this ML Comp, which if we look down here, it's meant to be sort of, it shows you as you're training all sort of the parameters and like the results you're getting out of your model. But it appears to be, I couldn't get this to work. It's just appears to be something that you need to install on your PC if you're like running the GPU locally. If you're using something like Google Colab, it doesn't seem to work. With regards to actually using it, yeah, so this is like a notebook I've created which does the segmentation sort of using their examples. So I was just going to run down through this. Basically, Catalyst, it's like FastAI in that it sits on top of PyTorch. It's just a sort of like wrapper on the top to sort of make it easier to run the training and certain functions. So it would be like FastAI or like Keras or something on top of TensorFlow. The one thing I'd say about it would be it's like sort of like a lower level than FastAI would be. FastAI, it's got like a lot of convenience functions for like opening images and like handling images and stuff. Whereas here, yeah, so here in this notebook, this starts off, so here I'm pulling the data down from Google Drive. I use this gdown. If you go into your like Google Drive, you can make things public and then you can use gdown with like a unique code, which means that you don't need to like have signed into Google Drive to get the stuff, and it seems to be more reliable and faster.
So Steve, sorry, question on that. So you're saying that gdown is like something that you can download it and use it. It's like a tool for Google Drive.
Yeah. So if my Google Drive comes up here. Yeah, so here's my Google Drive, and I've got a steel segmentation folder. Yeah, so like these are the images that I've downloaded from Kaggle. So you can go along And yeah, like right click on some of these and then you do share.
Yeah.
And it gives you a link, which is the code I was showing you before. Yeah, so like this is just this number here then, this hash value.
Okay.
Yeah, so like normally here I would like mount the Google Drive, which then lets you just use it as a normal drive, but you obviously have to go in there and you have to every time you got to click to enable that and to allow it to run. Whereas like here with the gdown thing, if your file is made public and you've got this code, then you can just pull the files directly. And as I say, I think it seems like faster than the other way of like copying stuff over. So it does, maybe marginal or whatever. It still takes like it.
I think gdown works with the URL also. I've used it before. You can just put the URL you copy from your Google Drive, and then it's a command that you can go from the command line, and then it downloads.
Yeah.
Like wget.
Yep. And like Catalyst actually has its own sort of version of gdown as well. If you look at like any of their notebooks, it's using a similar thing to this where it's like pulling data from Google Drive. But yeah, I didn't find when it like works, it sort of puts out information about every file that's pulled over, and I didn't find a way to do it without doing that. So it ends up like fills your entire notebook with output, which was really annoying. So I've just gone back to this one. Yeah. The other thing about Catalyst I found is it's very easy to integrate other libraries into it. So here you can see like, so we're pulling over Catalyst itself, but then like we're pulling across the augmentation library, not sure how you say that, albumentations or albumentations or something. And yeah, like the segmentation models library. So this is what the segmentations model library, I think I've got a link to it somewhere. Yeah, it's this library here. So a lot of people used it within the competition. As you can see, yeah, like it's got all of these segmentation libraries here, which is pretty much what we've covered, like, and been through all of these. You can see it's got like the Deep Lab V3 one. It's actually got Deep Lab V3 Plus as well. I tried both of these, but neither of them worked particularly well. But they're there if you want to take a look. In terms of actually using Catalyst, so in this function here, within the Steel competition, as you know, like they've changed sort of the format of the submission files and the format of their training files since the competition actually ran. So this function here is just something I've written to put the submission files and the training files back into original format. And yeah, so here, as I say, FastAI has like loads of sort of built-in functions for displaying images and stuff, whereas Catalyst, as far as I could see, doesn't have those. So you need to sort of make your own functions to show images. Yeah, so here it's just pulling like the images in and like using the functions matplotlib to display things. Then it also, I'm not sure if you've used sort of PyTorch itself, but the data loading mechanism in Catalyst is basically just PyTorch's data set and data loader. So with here, this is like the segmentation data set that they're using, which basically, like the main part of it is just like the get item, which gives you a single item back. And if you've specified any transforms, it applies the transform. Here I had to like, move the red, sort of the order of the bits about to get the colors to the start, to get the channel at the start.
So this class is from Catalyst.
No.
Or is a class that you extended from the data set. You did it by yourself.
Yeah, so I've done this, but yeah, I just took it out of a notebook from the Kaggle competition. But yeah, like this data set, it would work in like it's just a PyTorch data set. It's not specific to Catalyst.
Okay.
But yeah, you can see, so it just derives off PyTorch's data set base class.
Okay.
Yeah, so as I say, they use the Albumentations transforms, which, yeah, I've been playing about with those all week. They seem really good. Like there's like a stack of them. There's about 40, 50 different transformations you can use. So yeah, so here you can see it's, no, you can't. Oh, you can, yeah. So here, yeah, there's like transformations going on, but they don't seem very exciting, these ones. It looks as if it's just like sort of horizontal flip basically happening on those ones. So on the left-hand side is the original image, and the right-hand side is whatever the transform's done to it. Yeah, so this is a transform function. The one thing that they do use, Catalyst seems to be set up for sort of putting your code into production, and like it's pretty good compared to FastAI. They use YML files. I'm not sure. Oh, that's lost my YML. Basically, yeah, so for each sort of configuration, I think we've got one here I can show you. Yeah, a lot of people, rather than using Jupyter notebooks, a lot of people just have like Python code in the background, and then for each model they can use one of these YML file configurations, and it means that, yeah, so the whole setup of your model is described by the YML file. So here it's just showing you where the data is, the model that you want to use, how long you want to train it for, etc., what transforms you want to apply to it, etc., like all down to like the loss function, the optimizer function. So it means that like each model is tailored, and like each model is a sort of unique configuration. And then when you come to do like your ensemble at the end, it keeps the configuration with the model, and so it's very easy to ensemble things. So I think these YML files, you can probably use them with FastAI as well, but yeah, like it seems a good way to sort of separate the configuration out of your notebook. Yeah, so it's using this edict thing. So this one here, you can do it like in code, or you can pull the YML file in from disk.
So the YML is per model, Steve?
Yeah, so, well, it's not specifically for a model, it's for the whole setup of it's for the setup of the model and the setup of the data, and to describe what you want to do in training. So it's for like one particular experiment. So you can see here, it shows you where the data is coming from and how many classes you've got. Then it's got the information about the model. It's got the information about how long you want to train it for. And yeah, like any transforms, it describes what you want to do. And
so it's
the loss.
Almost like in fact, like a config file for your training loop for your entire training.
Exactly, yeah. Yep.
So you could, that's why you're saying you could easily ensemble, because you could specify multiple models to be trained, each model having its own config, and then the training loop just ensembles each of them at the end.
Exactly, yeah, because that's actually what I do when I submit to Kaggle in this competition. That's what I'm doing. It's from the notebook that I got. So it's got like 3 classifiers, and each one has like its own YML file, which describes exactly how that experiment should run for that one model. And when it comes to ensemble, so it loops through the 3 classifiers, loading one YML file at a time and running each experiment, getting its results, and then taking the average of those. And then it does the same thing with the segmentation models it has. And so yeah, so like each each experiment is sort of by itself and uniquely contained. So you can put the whole description of the experiment into it.
Interesting.
So each is that right? Each experiment is one YML file.
Yeah. So so here's my configuration directory.
Okay.
So you've got like a base configuration which you can use to say sort of where common things are. Then there's a classification directory. So here I've got sort of 4 setups for 4 different classifiers. You can see here. So like I've been classifying using like a ResNet 50 and an FNet and a ResNext 50 and stuff. Or like in the segmentation, I've been using all of the efficient nets like ResNets and the PSP net. So like each one of these, it can use like a different model, and it can use like different transforms, and it can use like different like sort of epochs and stuff for training and stuff. And the whole experiment is specified in each one of these files.
So Steve, it's so the YML file, it basically specifies or encodes a repeatable. It encodes instructions for a repeatable experiment to build your model. Is that what it does?
That's exactly it, and like that's actually how they sort of describe it themselves on their website. Like they say, like what they're aiming for with Catalyst is the ability to like make things repeatable and easily repeatable, which these YML files do. So I found them to be pretty good, but I'm sure basically it is just using like a Python library to load them in. So it's not something that's specific to Catalyst. It could be used within FastAI as well. But it is a good way to keep things in one place and describe the whole experiment. Here, like in this experiment, so these are the loss functions. Again, these are just like sort of coming off like the PyTorch drive base class for those. Catalyst also lets you set up a TensorBoard. If I'd like turned this on, you can use like TensorBoard to monitor the whole experiment. Although I never bother with that because I don't really want to sit there for hours like looking at the loss going down. So the important bits are setting up your data set which pulls in the single image. If you're doing segmentation, you also need to do the same augmentation on the mask as you would do on the image itself. And then you, just as like in PyTorch as well, you create like the data loader. So the data loader takes the data set and basically just like says more information about it, like the batch size you want to do, etc. So like it's actually the data loader that sort of pulls the data in for the training. Here,
a quick question. With the YAML file, you mentioned a specific loss function, right?
Yeah.
And do you need to implement that too in your Colab notebook, or does Catalyst know if you're talking of BC dice loss, it will grab BC dice loss from the library?
No, you need to tell it. So you need to have like a link between that name and which one you want.
Okay.
So you can see here we've got like BC dice loss.
Yeah, so you have defined it also. So that's why I was just wondering. Okay.
Yeah, so there's a
Okay.
function in the config that relates that name to this function here.
To what function? Okay, cool.
But yeah, so you just need to sort of wire it up so that you can use any of the ones out of the library.
The Catalyst library per se doesn't have one?
It has like a load of loss functions in there. But you can see here, in this case here, you can see like I've got like something that's a combination of like BCA with dice loss combined. So the dice loss is something like I've taken that's just derived off the standard module.
Okay.
But yeah, like its root bit is using again like just PyTorch's BCA.
Cool.
But there are like, if you actually look in the Catalyst library itself, they've got like a load of stuff like this, which are their own sort of specific losses and stuff. But mostly they are just.
Do you need to define?
No, you don't need it. Well, no, I've only defined this because of the fact, like within this competition, it's using.
Right. Okay.
Yeah.
Makes sense.
And because it's using like funny dice.
Cool. Okay.
And yeah, so and that's basically it. So once you've set all that up, then it all goes into this runner thing. So you can see these are all the bits and pieces all pulled together. So it's got like the model, which was here. So like in this case, it's the PSP net with a ResNet 18 encoder. The criterion, like that's just the loss that we're using. The optimizer and the scheduler, they just do, like in FastAI where it's got its like fit one cycle thing, which just describes like what happens, like sort of the momentum and stuff, what you want to happen like with your loss function and like the training parameters and stuff. And then the data loader, which is again the thing I showed you before, which is just the thing that pulls in the actual images itself. And yeah, like as with FastAI version 2, it's got the callback function. So somewhere in here, there's callback defined, but all they're doing in my case, I've got them set up to do like early stopping. And just like give sort of extra metric output. So that's about it really. So as I say, it's more low level than FastAI. You probably have to do more work yourself, but it's good in the way that because of the fact you're doing sort of more stuff, you're sort of closer to what's going on, and it's maybe easier to know exactly what's happening and to change what's happening.
So,
just a question. How, continue, Surinder.
Go ahead.
Okay, so how do you change? Because I believe all those configuration files and stuff Catalyst have, it allows you for faster iteration between models and do more tests in an easier way. So how do you change how do you change the backbone, the model you use for segmentation? Where do you change that on the configuration? So is this on the YAML you?
In this one here, as you can see, this one here, I've actually hard coded it to use PSPNet and ResNet 18. All you would do if you wanted to like run a loop with different segmentation models and different backbones on them, all you would do here would, instead of having PSPNet, you would just have the for loop, and like the for loop would read each of your configuration files, and it would take this name from the configuration file, and it would take the encoder name from the configuration file. In this case, I've just been like testing on one segmentation model, but yeah, so you would just basically set the loop up to read your YML files from the directory one at a time, and then you would, so like this one here, you would just pull the information from this model bit. So you would tell it just to use model architecture instead of PSPNet, and you'd use model encoder instead of having it hard coded.
Okay, and these models are from the TWIML implementation, or are they from Catalyst?
Catalyst does have some of its own segmentation models, but all of the ones here, these are the ones that I'm using from
that GitHub repo, right? The segmentation models by Torch repo, right?
Yeah, so it's from like that segmentation thing. But you can see here, like here, you can see it's like pulled the backbone in from PyTorch itself.
Okay.
Yeah, so in terms of being able to repeat experiments and run experiments quickly and stuff, yeah, I find it good. The only thing I would say is bad about it is there's very little support really within it. Within FastAI, you've got like a big community and like a lot of help you can get and like good documentation and stuff. Catalyst itself, there's very little help about, And the other thing is it's like actually sort of from Russia. So a lot of the help is in Russian. So
Wow.
it's hard to exactly sort of, yeah, like they've got like their whole, they've got like within Slack, they've got a Catalyst thing. But yeah, so you can see half of it's Russian. So my Russian's not too good. Yeah, the other thing that I tried then, as I say, it's just very close to PyTorch itself. It's just sort of extends it. And so within Catalyst, they have now added in the TPU support. But it is basically exactly the same as PyTorch's TPU support. So yeah, like this week I looked into like the PyTorch TPU. So this is PyTorch's example of like using a TPU on Catalyst, sorry, on Collab. So this notebook's just from PyTorch or whatever, and they just run through with the fashion MNIST example, setting up the TPU. So the TPU setup here is exactly the same as it would be if you want to do it on Catalyst. So they just pull in the latest cloud TPU thing. And then these couple of libraries, like the XLA is like the compiler for TPU. And then it's basically just a case of all of this stuff just sort of pretty much matches what I showed you from Catalyst, where they have like the data set and the data loader. And then when you finally get down to the bit of you want to train the thing, all you need to do is push your model and push your data onto the TPU, just as you would like stick them onto a GPU. Yeah, so not sure where the model is going here. So, yeah, somewhere in here they've got the device that it's going onto. Oh yeah, so here like they acquire like the TPU they're using.
So pretty much instead of reading the GPU device, you just pull in the TPU device and then everything is almost the same.
Exactly, yeah. So yeah, so this is actually, I've done it now. So this is like that steel notebook. I just showed you in this case here, it's like doing classification on the steel competition. But yeah, so it's putting it onto the TPU. Yeah, so you just like need to install a bit of extra stuff. So you need to make sure your notebook is obviously set up in the runtime here. Like so is it set up for the TPU? And then yeah, so all the rest of it's exactly the same until you get down to actually running the model. So you just need these couple of extra imports, and then you can see here, normally if you do like this device thing, that would return CUDA for the GPU, whereas here it returns XLA, which is the TPU's compiler. And then yeah, so here's the runner function, just as I showed you in the last notebook, but like this time, so you're sticking your model, you force it onto the TPU. This is the loss function again that goes onto the TPU. And the data loaders, I think, that already done that. But the only thing I found though was when I actually came to run these, the results I were getting was rather poor. So here, yeah, so this is the fashion one. So this is like training on fashion MNIST with the TPU, and you can see it took 540 seconds to do its training. This one here is on the GPU, and here yeah, so it took 101 seconds. So it was like 5 times faster on the GPU, but I have no idea
Strange.
what. Yeah,
Very strange.
The GPU I've got, like, because of the fact I'm on like Colab Pro, I always get like sort of whatever it is the best GPU that they can give you.
Is your batch size the same there?
Maybe.
What, sorry?
Is your batch size the same on both of them?
It's exactly the same notebook. It's the same notebook, apart from this notebook on the right has had yeah, just the TPU stuff taken off.
I see. Yeah, that was my question. I was going to ask you that, like, did you experiment with how big? Usually the main thing is that you can chuck a bigger batch size right now, right? And then it will train faster. So I was just curious about that, but yeah, that's weird.
It could be because of the fact it is, yeah, like a sort of a very simple problem, like doing the MNIST one. As you say, perhaps I could put the batch size up, but this is PyTorch's default notebook to illustrate it.
Interesting.
The one thing about it is that this notebook here, this is just using like a single TPU core, and they have another notebook here, which is this thing, which is like training on multi-cores, which gives you like 8 TPU cores. But with that, then you're into like a world of sort of multi-threading and points where you have to sort of get the data together and stuff. So I haven't tried this with the steel competition. Not exactly sure how long that took either.
Does Colab give you back multiple TPUs?
Yeah, do you even have access to multiple GPUs on Colab Pro?
It's multiple cores. Yeah. So there's 8 cores. So yeah, the other notebook just uses 1 TPU core. It says in here somewhere about it. I think it's like 4 TPUs and like each is a dual core or something. So you end up with 8 cores that you can run on. So you can see here like there's like 8 processes going on. But yeah, I'm not sure how you sort of tie them together and how you pull all the results together. So I haven't investigated that fully.
Yeah, you're right. It's 8 cores, and I think it's just it's at least what I've seen, you know, like from the melanoma competition. It's just you just replicate your data on the 8 cores, and then it, like, I didn't have to do anything extra to merge, like, you know, like to keep track.
Yeah.
I know, yeah, that's interesting. Like the single core is slower. Like I know everybody in that melanoma, they just stopped using GPUs and just were using these 8 cores, except the first place winner is the only person who, you know, could use PyTorch and GPUs and make it do a good result. But yeah,
the person that won the competition was using GPUs, not TPUs.
Yeah, but almost everybody else was like just using TPUs. And
were they using the TPUs on Kaggle or on Colab?
On Kaggle, and some of them on it wasn't very clear. Like, I think that's been one of the frustrating things. I know there are like 3 versions of TPU, V1, V2, V3, and it's very hard to find information like which one you have. Like I can't. Yeah, see, for GPU, you know this information, right? Like it's a test, whatever, NVIDIA SMI. So there's no equivalent NVIDIA SMI command for the TPUs, or at least I haven't found it yet. I mean, it should be there. Like.
Yeah, that's the other thing about Kaggle, though. Like within Kaggle, when you get a GPU, I don't think it's as good as these Tesla P100s or whatever. And so, yeah, like the GPU on Kaggle tends to be not the best. Whereas, like if you're running with this one here, it's sort of like a top of the range GPU, which is good.
Yeah, I rented something better. I rented a Tesla V100 on Wash.ai, and the TPU was even better than that.
Yeah. But as Rekla says,
Steve, on the back with respect to the YAML file, so if you mentioned that since it's tied to PyTorch, you could potentially set up a system that where FastAI could potentially, or you could write some scripts then that would read the YAML and stuff the appropriate parameters into FastAI, or did you mean that FastAI could currently use YAML files, but wouldn't you still need to write the translation of YAML into providing the appropriate parameters to FastAI?
Yes. So as you can see in the function here, this is like effectively doing like the YAML file in code or whatever, where you're just like setting up the data structures and putting the parameters in. Normally you would do it through the file's disappeared again, but normally you would do it through the file and just load the file in. But you can see within here, yeah, so something like here that there's just the parameter that's come out of the YAML file itself. So there's no reason why you couldn't do that in FastAI. You would just read your YAML file, read the parameter like this, and yeah, populate your FastAI structure in exactly the same way. So yeah. Okay. So using these
somebody
things,
could just write a YAML to FastAI I don't know, it's not a translator, but configurator or something, and then which runs on top of FastAI and can just go take a bunch of YAML files and convert them, and then you just need to be able. Then you ought to be able to run them like Catalyst.
Yeah. So yeah. So this here is like a FastAI file. So yeah. So somewhere in here, whatever, you would just read the YAML file first, and then into any of the parameters here that you wanted, you would just stick it directly into the FastAI function.
Yeah. In the new post for the FastAI v2 release, they put a small page on a small documentation on migrating from Catalyst to FastAI v2, and there they have a small library that you can use to quickly like move from Catalyst code to FastAI 2 code, but I didn't read it. Yeah.
All right. As I say, Catalyst, I don't think there's that much to it really. It's like basically just like a slight wrapper on top of PyTorch, just to give you like sort of convenience functions for doing the training and for sort of reproducing your experiments and stuff. But yeah, it is like sort of, it's easy to understand really what's going on within it, and it is quite easy to use and sort of easy to set up to have like multiple experiments going at once. But yeah, and I think that sort of FastAI, like now it's got in its v2, now it's got like the callback functions and stuff. It seems to have taken stuff that Catalyst has, and FastAI v2 is maybe just as good as Catalyst is now.
Yeah, except it still lacks what I think you were saying of easily combining. For example, the ensembling thing you mentioned, which you can do once you set up the YAML files, then you can, because it's almost like it's a layer on top of FastAI, which could be very thin again, but enables you to do setup of FastAI models and not just models, but setup of FastAI training loop, multiple of them to handle different models, and then combining them to form ensembles and stuff. So.
Yeah. This notebook here, this is the actual one that I use for doing the submissions. So yeah, just at the bottom of this, yeah, so you can see this is just the main function that starts everything off. So it just calls this function here. So in this case, it's trained all the classifiers already. Yeah, so all it does, it looks at the configuration path that you set up, reads all of the YAML files in, and then works its way through each of those, just pulling their configuration in and then doing the predictions, and then it just takes the average of the predictions and then does exactly the same for the segmentation. So, and like this is all coming out of the YAML files from all the models that are already pre-trained.
This is custom code, Steve, or was this from the notebook from Kaggle?
This is the notebook that I used to generate the submission file for Kaggle, but this here is just out of, I can't remember what it was, like the 5th place or 10th place solution or something. There's one guy, if you look in the discussion for the steel competition on Kaggle, it like has a list, and this one, yeah, it was like somebody that uses Catalyst, and all of their stuff's on GitHub. But because of the fact that yeah, like Catalyst is sort of set up to run Python files as opposed to notebooks, so I had to like play about with it or whatever just to get it into notebook form. But yeah, this is sort of like his configuration, and then I've just added more models on top of it.
Cool. Okay.
If you can post some of the links, Steve, whenever we are done, to the Slack channel, that'd be great.
Okay, cool. I'll stop sharing now then.
Okay, cool. Thanks a lot, Steve. That was very interesting.
So you're sharing your notebook on the link to your notebook on the Slack?
I'll put it on after this. Yeah.
Can you?
My notebooks are maybe not shareable. I'm not sure. Yeah, I'd have to make them public on my Google Drive or whatever. I'll see what I can do, but I'll put links on to the other guy that where I've taken most of this stuff from.
Okay. Yeah, but did you? No, it's okay. It's okay. You can send just the link of the guy there. You basically just took their codes and then put on the collab node format, right? Collab to work on collab, because
yeah, so there's a few things. It's like, as I said at the start, basically in the steel competition, for whatever reason, after the competition finished, they changed the format of the submission file and they changed the format of the training file. So if you just go to the guy's GitHub and pull his code, it'll not work. And also as well, he was using like an early version of the Catalyst library, so some of his like imports and stuff don't work. So I had to make like quite a few modifications just to sort of get the imports going right, and as I say, to sort of change it so as it would work with the new format of the steel CSV files. So
I see.
His code is good because it sort of like clearly shows what's going on, but yeah, you need to modify it if you want to actually use it.
Okay. Well, thanks.
Steve, one more question. So I missed some of the start, like the first few minutes. So like I was looking at the PyTorch segmentation models package, right? And when we see they're getting started, they have this you have to define your data set, like data set class, and do the get item function. So I missed the basic part. Like, what's the advantage of Catalyst over the PyTorch segmentation models?
The Catalyst is basically just defining your like whole training pipeline, whereas the segmentation models is just the models. So you can't really use the segmentation models thing by itself. You still need to write all the wrapper code around that to actually sort of run the experiment, run the training, and run the inference.
Okay.
So Catalyst is doing that bit for you. It's just the segmentation models has defined like all of those segmentation algorithms or whatever in PyTorch. So the segmentation models thing, you could use that in anything that uses PyTorch.
I see. Okay. Okay, thanks.
I think, Mayo, like if you're looking at the Getting Started notebook, that has the whole training pipeline sitting there. But if you like do what Steve has done, just bringing in that library, the whole benefit is that you just get your models from there You
I see,
use
okay.
Catalyst to set up your whole training pipeline. Your dataset data loader, irrespective of you do it either in the notebook with Kabble's GitHub repo, or you do it through Catalyst, you still have to set up your datasets and data loaders to read in
Okay.
data.
Great, thanks a lot, Steve. That was very insightful and give ideas. I think in the long run, if something like this can be combined, and as he says, if it's already in progress, and the Catalyst overlay, so to speak, on top of FastAI would be really cool to use that kind of powerful combination, because not only is each of the training steps then customized, then you can customize or twiddle the training loop and combination of training loops with multiple models. So it kind of gives you the ability to customize the training loop as a loop and then as multiple loops with multiple models and ensemble them easily.
Yeah, that's what I found. Like, as I started like testing sort of the bigger res nets, the batch size I had to use dropped. Otherwise, I was running out of GPU memory. So it meant that I could have like the batch size tailored for the ResNet model that was being used.
Yeah, so lots of tweaking at the higher level made possible. Okay, cool. Then Raquel, you want to share the PSP.NET, and we'll see how far we get, and if time permits, then we can jump into DLv3 Plus as well.
Yeah, I don't have DLv3 Plus. I have DLv3, but anyway, I don't think.
Oh, okay, whichever one.
Time to jump into that.
Yeah.
Which is PSP. Oh, okay, hang on. You guys able to see my screen?
Yes.
Yep.
All right. Perfect. Cool. So yeah, using FastAI v2, we kind of jumped in last time and we saw this where you kind of bring the data in. I'm using Camvid. I'm going to be using Camvid throughout, using ResNet 18, quickly perform just some quick tests so that we see the code running and we understand kind of what we have read from the paper and kind of matches the stuff that we thought was happening. That's kind of the purpose. No intention of using this for training. Cool. So
what's your tab count up to? I'm up to 80.
I have another 4 windows here, which I'm not sharing right now.
What do you have? How does it support it?
I love my MacBook Pro for that reason.
I'm the same, Raquel. I had to download an extension called the Great Suspender, so the other tabs would auto suspend because I don't close my tabs.
Yeah, I guess we all have the same problem, just at different extents. Cool. So yeah, so this all should look pretty familiar. Read the images in. This is kind of setting up where your labels or masks are coming in from. That's what the masks look like. An example of the values in that. We have like 32 values sitting in there. These are the different classes. Quick and easy way to specify what your, I think that is for validation. To set up your validation set, setting up your data blocks with the new V2 stuff. All that is all the same from before. Setting up what the metric is going to be. We've seen this also before. They have this weird white code stuff, kind of like a background. Not a background exactly, but those are some pixels that they didn't decide to label in any of the 32 classes. So that is what that void was. And yeah, so that's pretty much the standard getting your data ready sort of stuff. Jumping into, we saw unit last time, we saw unit plus hypercolumns. Now let's look at what PSP.NET does. Oh, can you guys see this image too?
Yes.
Oh, okay, awesome.
Yep.
So quick kind of repeat of what Srinivas had kind of discussed was bring in your input image, run it through any CNN. Don't go all the way down to classification, stop somewhere in between, get this feature map out. You use this feature map, pull it basically at different resolutions, and perform some convolutions, change your width. We'll kind of look at all this stuff, just quick run through, and upsample all these guys back up to the same as this size, put in through a skip connection. So you get this whole new stack of images. Basically, in essence, it is looking at different resolutions and your original feature map. And this is like 8 times smaller than the output. So you perform this huge upsample over there, which is like 8x upsample. So I did some labeling there with kind of in correspondence with the code. So we can kind of keep looking at this code and this diagram. So hopefully things should make sense. I'm going to kind of squeeze this somewhere here where you can still see it. So cool. Oh crap, can't do that. Okay, so PSPNet, we start off with initializing weights. We know that we're going to use chiming to initialize stuff. This is again pulled out from FastAI V2 just to see what is happening there. So first define the pyramid pooling module. So that's what's going on over here. So what we should be looking at for is you bring in your image, that is this feature map of what is coming. And you need to apply different pooling ratios, right? So you'll have like pool of 1, pool of 2 by 2, pool of 3 by 3, and pool of, I think this is 6 by 6. So that is what is happening over here. Pyramid sizes basically is 1, 2, 3, 6. And you pass that in for different sizes of that pyramid size. You basically first perform this average adaptive average pool. So that's what brings this down to this size. Now you have, these are the number of filters that it has, right? And the number of filters wouldn't have changed from what the feature map was. You're just you're changing basically spatial resolution. You're not affecting the depth in any way. Now you perform these convolutions to kind of get the channel sizes down, and basically you're trying to add some more convols there to gain a little more information sort of thing. And the way this is done, if it's no, okay, that doesn't still come here. Okay, so this pyramid pooling is just pretty much that. So you do the adaptive average pool, perform these cons, which basically changes input number of filters to this output number of filters. So that's basically reducing the number of size. And we'll further look that the way this reduction dim and in dim are kind of related is kind of reduction dim is equal to in dim divided by the number of these scales that you're using. And the kind of the general idea is that if you so in this case you have 4, so let's say you had 16 of these filters coming in. So you would say that each of these give me 4 of these filters, 4 of these, 4 of these, 4 of these. So when you kind of stack them back up, this will again become 16. And you'll be like, started with 16 and you'll have like 16 plus 16, 32. So that's kind of the math that I understood there. Stick your batch norm, stick your ReLU, so all that is your general. Sorry.
Ricky, quick question. I haven't recently looked at the PSPNet. Do you remember whether they did the batch norm? Because the reason I bring that up is the DeepLab V3 and the HRNet guys, or at least the DeepLab V3, V3 Plus, seem to make a big deal of adding batch norm somewhere along their evolution.
Highly possible, but yeah, this I've mentioned this here. I pulled it out from this repo. I'm sorry, this is the guy repo. So this is from the ArgSys that you guys shared before, and they have. I would imagine like if batch norm works, they would have stuck in the batch norm. This is not like a exact implementation of what the paper is, especially in terms of like the batch norm stuff. I'm really not sure if the batch norm.
Yeah, no, I'll double check. I was just curious whether you knew, because that was. I mean, it's obviously it's so obvious that you would stick in, but sometimes
Yeah, I guess it was before the batch norm time, and I think I remember clearly that was a difference for V2 and V3. I don't remember, but PSPNet I guess is older than that, so maybe they didn't.
Yeah,
not sure.
So maybe they just had it always, but I'll check. But I was just curious because it's an obvious thing, but then again, obvious things could be saved for it. One more rev of the paper too.
Right. Yeah, I don't think there's a batch norm. I don't see a batch norm, at least anywhere in their paper.
Is this the paper?
Yeah, this is the paper.
Oh, they do have it then, because if you go to the left, it just caught my eye.
Oh, I did?
Yeah, because if you go down implementation detail, DDD, and somewhere on the left, I saw just before you moved off that they
weird.
talk about batch now.
That is, come on there.
If you even search for batch. Oops.
Yeah, my Mendeley search is kind of weird because it does a document search as well as everything. Anyway, I guess we'll get back to that. No, I don't think that's gonna work.
Yeah, okay, never mind. Let's keep going.
Yeah. So yeah, so basically all we've done is this part is what is kind of built out here. That's the pyramid pooling module. So that part is ready. So just to see what is again happening here, if you look at the diagram, out is equal to, initially out is equal to just this stack, the first one that is the skip connection. And you run through all the features. You need to interpolate because you need to kind of bump this size up to this size. So that's why you have all of them kind of becoming the same size. So that's what is happening over here. And you keep concatenating them. And then this whole thing becomes your output right now. So that's kind of pyramid pooling module. Any questions there, or can we move on?
No, cool. That's very clear.
Sounds good. Okay. So yeah, define this PSP net simple, straight. This is what I was talking about, the pyramid sizes that get passed in 1, 2, 3, 6. That's what you can look exactly matches with the adaptive pool sizes over here. Oh, what else? Nothing main there. Okay, so usual, you use the backbone or the encoder or the feature representative, whatever you want to call that. Use FastAI's cool create body stuff, which basically cuts off everything from your pooling, last pooling layer and down. Whatever backbone, so we'll be using ResNet 18 over here. So I'll basically get the backbone. So that is kind of somewhere here in this image right now. We're kind of talking something over here. Then, yeah, this is just so that I can kind of hook into those modules with FastAI. So you can get what the activations are. And okay, so this is kind of the interesting thing with PSP.NET, right? We saw that they used this aux laws, which if we look, there it is, where they said that we won't be just going all the way down and using the final mask and take the loss with that with respect to your target. We'll kind of branch out intermediately also and look at the loss there, kind of something like what's used in Inception. So that is what this kind of points at, which index you want to kind of peek into and look with hooks. So what else is there here important? Okay, yeah. So this, we kind of saw what dilation and padding. Actually, we'll see dilation more when it comes to DeepLab V3 for the true convolutions. And I think Antonio was the one who asked that question, like, how is it that you still end up getting the same size on the output, even though they're doing all this dilation stuff? And then the key was basically, whatever dilation you do, if you do the same amount of padding, you'd always have like a valid number of convolutions to give you back the same size. So this is kind of an interesting thing that I found. You basically keep those two the same. So that's kind of just setting those things up. Nothing else happens over there. What else? Okay. So you get your different feature sizes. You need these feature sizes so that you know how to like bump this image sizes back up when you pass that through. If you hook into the last layer of this model sizes, we would have actually gone down the encoder. And it's the encoder, so you don't have any of the classification stuff. So the last layer's size, if you look at, will be the size of the h by w by width, h by w by depth will be equal to this feature sizes. Here you'll get back just h by w. So what else is happening here? So this is what I was saying. So this in dim over here is basically this last -1 index is the last one, and you're just pulling out what the number of channels on that is. And this is PyTorch stuff. So batch size, channels, height, comma width. So that's why 0, 1, 2, 3. So channels is 1. So you're figuring out what the dimensions of those are.
So,
So you get,
so you're saying that feature size is the last, is you're just getting the very last feature size. That's why
exactly.
feature size -1. And then of that, the first dimension, why is it? Oh, because the 0th one
Batch.
is the
Batch.
batch size.
Yep.
Okay. Then it's the first one is your channels.
Channel, exactly.
Okay. Got
So
it.
that's what. So this num channels will correspond to this endian or num channels.
Yeah.
So that's what you're getting. So that in essence is kind of your input to your pooling module.
Right.
So we'll be using that. And this is this penultimate channels is basically this calculation that we did, right? So I don't think this is a necessity, but the approach they were using is like, let's say you had like same example, 16 filters here. And they're saying that this stack that you add on, let us make that total sum also to be equal to 16. And just to do that, the math works out that you need to divide 16 divided by the number of times, number of different scales you're looking at. So 16 by 4.
I think in one of the deep lab things, so they violate that, but
No, probably, yeah, that's what. I don't see that being, yeah, I mean, I could not remember anything, but yeah, I'm not sure why exactly.
But in this paper, yeah, they make a point of it that,
Okay.
they try to keep the number the same as NDM as you've shown here.
Right, okay. So yeah, so that's what basically this calculation is doing. So you're taking whatever your input number of channels are, that is this divided by the length of pyramid sizes, which would be 1, 2, 3, 4. So 16 by 4, let us say, for example. Pass this off to the pyramid pooling module, and that would generate all this stuff. You would end up here. So that's pretty much it. We kind of covered this. We kind of covered PPM. Now let's look at the last part of it. So you kind of form this stack, and now you have this huge upsample that you need to do, and they squeeze in a bunch of convolves here to kind of, I don't know, retain information or learn information. So what is happening here? Define this final, which is nothing but okay, this whole thing. I'll bring that image back up. I hope that doesn't go crap. Okay, anyway, you saw what I marked, like all the way, this whole thing would be penultimate channels into pyramid size, which should give you the sum of this plus num channels is basically this. So that is basically saying 16 plus whatever each of these individual ones were into the pyramid size. So that in whatever calculation we were trying to do, that was like 16 plus 16, this will end up with 32 channels coming in. You want to spit out the 16 channels. Again, no reason for that. You can drop that number down and just stick 2 convolves in there. So they just, I think even Jeremy does that, like with the typical unit in the between of the encoder and the decoder, he stuck in like a couple more extra convolutions there so that it could learn more stuff. And then at the end of it, we know that if you need your output image for segmentation, we always do h by w comma number of channels, where number of channels is basically equal to the number of classes you want to predict. So that's what this last convol is. Penultimate channels output is splitting is basically number of classes. Aux logits, again, where did we hook that to where is that? Somewhere we did -2. Okay, yeah. So this is that last part one. Yeah, last part one layer is where we're hooking in to get the aux logits, and you perform again one more convolution with the aux logits there. Again, same thing. Since you're finding a loss with respect to a segmentation mask, you have to have like your output number of channels is equal to number of classes. That's pretty much, and this actually forward runs the exact same way as what I've explained, but you have to quickly look at it. You find the original size of what your feature map is going to be. Or is this feature map, or is this, oh no, actually this is the original input. So it's the size of this input image. Then you run X through your backbone. So we did this part, ran it through CNN. So now this final X that we got would be this feature map. Now, that's the other thing in this is that during training, we use both the aux logits are being rather only during training is the aux loss used. During inference time, the aux loss branch is not used. You just predict straight down. So we got our feature map here. If it is training, we'll calculate our auxiliary logits. Then you run through the pyramid pooling. We did that. Then you run through your final so that you get that. That is done. Now you're basically, again, this is if self.training. Yeah, so I've written both of them out here. I was just having some trouble with FastAI initially. If you're doing no aux loss, you're just returning one loss back, right? So that's what this F interpolate is. You're bringing back this interpolation would be doing actually this to this, so that from here to this. So this is that, if you remember the paper, it is like an 8x sample. So that's what this interpolation is doing over here. That's why you need this original image size. Now it makes sense. That's why we kind of calculated that here, because whatever final mask you get, I mean, the final image you get here, that should be bumped up to a size that matches this size. So that's why I stored that size there, okay. And then if you uncomment that out, run this guy has the same loss, which is at the end of the line, and you have the aux loss also being added onto it. So you have both the losses. And if it's not in self.training, that is basically eval, you just use one of them. So
sorry, what did the excise 2 onwards do? And
this one. So yeah, okay. So basically, if you look at this image, again, first let us look at what the excise would return now: batch, channel, height, width. So excise 2, and so on. I'm sorry, 2 and so on is basically going to return height, width.
Okay. So you're just modifying the HW and leaving the channels alone.
Right, exactly.
Okay.
You're trying to, because you would get a certain, so actually till this stage is here. So you would have whatever the channels that are coming in, which is these number of channels. So like in our running example, it was like 32 channels coming in, let's say, which is actually a very bad example because our n classes is also 32 in this case.
Yeah.
So anyway, the output would be 32 channels, but the height and width will be like smaller than this. So you're just bumping that 32 channel H, W to 32 channels height and width of this original input image. So that's all is happening over there. You do that with your aux loss also.
Sorry, one request. You had mentioned there was a little bit of, you had a little bit of trouble getting it to work. If you could mention where the problem that
we'll go down when we look at the loss function. That's exactly where I'll point that out.
Okay.
So yeah, when I share this notebook, just keep in mind that you can run both of these options, like no aux loss, with aux loss, done both, and I see with aux loss slightly improves the results. But yeah, I haven't done any extensive stuff. We're on it just for like 2 epochs.
Yeah, no, I was more focused on, sometimes the mistakes teach us more about what to look for and stuff.
Yeah, we'll surely do that. I'll show you. Yeah, I have that written. So yeah, so that was kind of the model. This was just, again, defining some meta stuff. So architecture, like we said, we'll be looking at ResNet 18. Cool. FastAI 2 stuff tells you where to cut. So this is where the backbone is kind of gathered from. You have your stats, all that stuff is sitting in meta. Number of inputs we know is the 3-channel RGB image. You're using pre-trained and out. Again, you can use FastAI's getC on your data loaders, and that gives you 32 channels. That's 32 classes that we're going to be predicting. So here comes the thing, like, as far as I know currently, I didn't know how to work with these those 2 losses coming back from the PSP net when you're training. So I had to go make a couple of changes here. And so this is again pulled out from FastAI. I don't need this diagram anymore. Okay. So yeah, this is the base class law. So the way I think Jeremy and Sylvan have kind of done this right now, I think this was not there in V1. This is V2 stuff where they have this base loss class from which all the other loss classes are kind of they inherit from, and then they just add bells and whistles to that, where you see this, you usually never see a decodes and activation, and those things also kind of stuck on along there. So if you look at this base loss is where all the main kind of grit is. And lots of things will like look very familiar from V1 in terms of we're going to be flattening our loss. He's going to be changing, discussed this a couple of times before, how we change the channel, batch channel height comma width to batch height comma width to channel, and then like flatten the whole thing out so we can use it consistently, irrespective of whether it is classification, segmentation, or whatever we're trying to do. The changes made were kind of here. The way they have it defined is if it's self.training, you kind of would have disregard all the copies. First, let's look at if it was just input 0. So the way it was defined would have been if it's self.training, grab your input, transpose this, make it contiguous. This is so that we can flatten it to get it in that order. Your target is brought in again, and where is it? If self.flatten, this is what I was telling you, change kind of the shape. You move the batch to the last dimension. You move the channels to the last dimension, and you kind of get your new 1D kind of structure, which is flattened out, which can be now compared with target. And whatever your loss function is, you basically call that function and pass these two things in. So this is kind of how the base is defined. And if you had cross entropy loss, that would basically be this function call, which would take in this input, this target, and would perform your cross entropy loss.
And just to refresh, the flattening is so that you can do it independent of the HW. No, independent. This is what I always forget. Independent
of batch size, height, and W actually.
So yeah. So independent of BS, H, and W.
Yep. Exactly. So this is what would come back, and he rearranges that to W, height, channel. Now, if you look at this, it is basically batch size into width into height, channels. So this really doesn't make any difference now, because it's kind of like, imagine if your image was like half the size of what it was, or it was twice the size of what it was. If you flatten it out, it really shouldn't make a difference in terms of comparing pixel to pixel. Same way, batch size doesn't make a difference if it's one image or two images, you're stacking everything up. The only thing that makes a difference is the number of predictions you're making for a pixel. And if you kind of draw parallel with classification, that's what kind of happened there, right? If you were distinguishing between cat and dog, your channel is kind of 2 over there. All you care about is whether you're predicting, I mean, wherever the weight is high, whether it's on the first one or the second one. So that's kind of the parallel that is going on over there. Does that make sense?
Yep, I'm just refreshing my memory because they did so much for Serastal, right? Throw everything into the first, just focus on the channel because that's what tells you the classes.
Right, exactly, yeah. Cool, so that's that. Yeah, so this cross entropy loss, the way it's defined in FastAI V2 has this decodes and activation, so that kind of helps you. Decodes, like the name suggests, is basically once you get these channels, you pick an argmax, which will give you what the class exactly was. And we always ended up with like 32 channels, right? So there was some way before you pass it into cross entropy. I mean, cross entropy would do the softmax within the cross entropy loss function. But if you have to like get out the probability values, then you need to apply the softmax to it. So that's what you're specifying exactly what the activation is. So that's what these two kind of cool things help you. I mean, FastAI helps you do that. Now the difference of what the change I had to make was, for some reason, I was not able to get it running with self.training and when I was passing in both the losses together. And I don't know, the easiest hack I could find was if I am passing in, so I'm passing in the tuple, right, of my losses. Let's go quickly look at that. So I'm passing in a tuple of losses if I'm comment this line out. So versus if not, I'm just passing one loss in. So all I did was, if length of input is equal to 2, which is basically self.training, then do this. Basically, you're just looking at both these losses, treating them like individual losses, and that's all you're running. You just storing them in 2 different variables, do the exact same thing, run your losses, and then just sum them up.
It seems like somehow FastAI's coding or infrastructure assumes
one loss.
Somewhere baked into it is a single loss assumption.
Yeah, that's the thing, because this actually comes back as in. That's how it's defined. So I don't know. I'm surely not good at the coding part of it. So I really don't know what the understanding behind is there. But yeah, this was a quick hack that made it run.
Mm-hmm. Yeah,
so
makes sense.
Going ahead with that, yeah. So that pretty much I think is the whole thing. Yeah, and then here again I have a bunch of other things like if you're running no aux loss, just one of them, you can straight up use this loss function cross entropy loss flat. Important thing is, again, you need to kind of pass your axis is equal to 1, which defaults to -1. So axis is equal to 1 is basically telling you it's the channel axis that you're trying to basically pull out to the last, this whole thing that you're trying to pull it out to the last, and you're calculating the loss across that. What else? Yeah, then it's just back to, again, FastAI2 stuff. Actually, this pass in your size, your pyramid size is 1, 2, 3, 6, whatever that is required for your pooling layer. Create your model. After you create your model, create your learner, pass your model into that, pass your data loader, pass your loss function, metric, all that stuff. And yeah, fit one cycle and let that run, and it works.
Cool. So do you recall what incremental benefit you said you did see a benefit because of the aux loss?
Yes, it was minor. I ran this again yesterday, so I might have changed something. So I don't want to say anything for sure. Yeah, I don't remember right now.
But it wasn't.
It wasn't. Yeah, like to go back to what we were talking about. Like I really didn't see any significant improvement in any of the models that we have trained compared to the original unit. I mean, the dynamic unit.
But yeah, which is kind of what. Of course, the ensemble for Steve kicked in.
Yeah, that probably me. Yeah, the ensemble.
But the individual stuff, Steve, were you also saying that individually you didn't see a very substantial improvement compared to the dynamic unit, or you did see it in any one of the models that it was better?
No, PSP didn't work that well for me. The one that worked well for me was the feature pyramid network. Basically, the unit with the efficient net backbone and the feature pyramid network with that. But I do have like a PSP net in my ensemble, which came from the guys thing, but it would be the worst out of the segmentation models.
Yeah, it wouldn't be surprising or shocking because to a certain extent, this 8x upsampling at the last kind of kills. I would think the benefit you get from what they are doing with this tracking, but that's where, to Rekil's point, and Rekil, maybe in the remaining time you can talk about a couple of tweaks you mentioned. So that's where maybe some combination of ideas might actually boost it, because obviously meaning the PSPNet paper, does a good job of introducing the idea of the pyramid pooling, which again Deep Lab takes off from that, but it, on the other hand, they drop the ball on how they get to the final result by not doing any encoder decoder is not used, and they just kind of blindly upsample.
Right. So that's what. So there's a cool thing because of FastAI's dynamic unit. We can kind of look at this next time. Is we can take this whole stuff that we looked at right now and stick this into a dynamic unit, and it will automatically create the decoder for us. And you can train and see on what those results are.
So when you say stick this, meaning where? So that we'll look at maybe in the next.
Yeah, the details. Yeah, but that's kind of the just general gist. Like basically, this what's kind of missing here is the decoder, right?
Yeah, exactly.
So you kind of append that sort of towards the end, and that's how you kind of grab towards that. I don't think if I have a quick implementation on
In the unit decoder, it has like all the cross channels, doesn't it, from the encoder stage? So how would you fit this into a unit architecture and have the cross links?
I'm not clear with the exact details, but any of the cross connections, this part wouldn't be touched at all, right? The cross connections would come from this CNN. So the backbone is where all the cross connections would come through. So kind of treat this like at the bottom part of that unit. So there, this kind of is treated.
So it would be the very last before you
start up sampling.
Yeah, start back up on the path, and you just generate the output to, or I should more appropriately say, thinking of the DeepLab V3 Plus paper, you kind of take the output of this convolution which comes out as the input to your decoder and go back up.
Right? Correct. Yeah. That's what my understanding is also. We can look at the details. And go through it next time.
But that's essentially like you could write a paper like PSP net V2 plus.
With the decoder implemented in it. Yeah. There's a couple of interesting things that actually next time, or I don't know, next time also, maybe the time after that, I tried out a couple of things from DeepLab V3. We saw how we encountered dilated convolutions and how they helped us, right? So I just went ahead and like changed the unit, the same dynamic unit that we saw, and basically added in this Atros spatial pyramid pooling stuff over here. I was just keen to see if it will work. It worked, but accuracies.
By the way, did you have to do the padding stuff that you were talking about to keep the same size, or?
Yes, I passed that in. Where did that go? Here, the padding and the dilation is kept the same. Okay. So you pass that in, and that can. So obviously it becomes a bigger architecture. So I had to drop my batch size and all that kind of stuff. We'll look at it next time. And we can kind of pick each other's brain and see why it didn't perform or what are the changes we could make. Bottom line, it was pretty easy to kind of squeeze that in. So now since we've gone through so many papers, I think we should maybe spend some time like kind of intermingling things from one network to the other network, making it smaller, making it bigger, seeing how it performs, sort of a thing.
Yeah, no, I think, and then you could, obviously your basic unit also has the ability, the dynamic unit, to apply, the other couple of tweaks that the dynamic unit has, which is also good, is it has the ability to bring in self-attention.
Right.
And it has the ability, which I think combined with things like PSPNet or DeepLab would be very extremely useful for PSPNet, for example, is this whole, forget the terminology is always, the sub-segment initialization and then upscaling, which the dynamic unit does, that Tammy went through in great detail in one of
the ICNR, the subpixel.
Yeah, the ICNR and the related initialization or the subpixel.
Yeah, pixel shuffle.
Right. So that's another thing where I think it would be very useful for object detection as well as for small object boundaries, pixel image segmentation.
Right.
Because it really helps at that sub-pixel level.
Correct, yeah. And I think there is one more thing. I don't know how many people in the group would be interested. We keep going back to attention, whether it be image processing, NLP. I feel we should spend some time and look at attention. Just to understand what's going on. And the ridiculous thing about attention is like, there was some part where I saw, I think this is a 2020 paper. I think I got the link from, I think, what Antonio shared about the HRNet stuff, and he makes a mention of this. Just to see in essence what is happening here is that you have your original image. These are the course labels that someone would have labeled, and it is able to auto-generate these pretty fine labeled stuff. And now you can use this and this for training. And I mean, for me, personally at work, this is super helpful because I have to sit and label otherwise, like face, skin, hair, nose. So now I can just do it rough. And if I can implement this, then I can pretty much get it to this side, which I think is pretty cool. I don't know how many people are keen with that.
No, I think that particular attention paper we discussed as part of the, the GAN attention, which was used by Jeremy when he implemented the dynamic unit, refers to that. And so, yeah, I think.
Yeah, I haven't seen the code for GAN.
Sorry?
I mean, for self-attention. So I don't know how it works exactly. So I have that on my to-do list.
Yeah, it's there actually on, he just adopts the paper's code in the dynamic unit stuff. And it's fairly self-explanatory if you go through his dynamic unit code, which then swallows in the self-attention from the GAN paper.
Oh. That is interesting. I never saw, like, self-attention or attention is basically just a parameter that just gets sent off.
Yes, but that when you turn it on, when you then I spent some time going through that paper and understanding what it did because of the overlap with the language model, because I didn't quite get how you apply attention concept to images. And it basically is very interesting because it just takes and spreads it across the entire image.
Yeah, so basically this is what this is using attention. And the idea here is that this is your original image. And they are saying that, see, at different scales, this is at 0.5, this is at 1x, and this is at 2x. At different scales, different parts of the segments are being able to be correctly labeled. So they specifically talk about how you miss out the poles, whereas the poles here are very well represented. And again, here they're very well represented. So if you look at the attention map over here, the sum of all these attention maps is equal to 1. But you see at different resolutions, the attention is, the white is where the main attention is. So you can see the white is getting focused on different parts.
But it makes sense, right? Because it basically brings in the PSP.NET, or it brings in the concept, it overlaps the concepts of PSP.NET, deep library and stuff, which is at different scales, the image gives you different different context or different high-level semantic information. And therefore, when you have different semantic information, your attention will focus on different semantics.
Right. But it's just
so his original, the GAN attention paper was at a single level of the full size of the image.
Right.
And this one just extends it from what you're saying, and it'd be great if you can post the link to that on Slack. Yep. The same thing at different HW or different resolutions.
Mm-hmm.
And what's fascinating is that at different resolution, from what you're saying, it seems to change its attention to different contexts, or therefore different objects are differently emphasized.
Mm-hmm.
Which is fascinating because, if you, and it's kind of interesting also because when they dive into why attention in natural language processing helps you so much, it's because the underlying thing that it does is it is able to break up the composition of, or I should state it differently, what they have found is that language is compositional as well as something else, meaning, you put the words together, and then as you put them together, the meaning of each word changes. And this attention mechanism seems to be able to capture that better than anything else. And if you see that, or if you read those papers, then, from reading those papers, you should have had the idea that at different levels of resolution, you will be able to get different things from the images. I don't know whether I'm making a whole lot of sense.
Right, yeah, that totally makes sense. The interesting thing with this is that they do this during training. I was only thinking of it mainly at like inference. So they have with this attention mechanism, again, the right-hand side experiment kind of shows that how that the divider of the road kind of at the higher resolutions gets kind of messed up, whereas at the lowers is kind of well retained. they able to, yeah, correct. This is how they managed to somehow train with all these different resolutions, and they managed to get this much more higher score output. With the interesting thing for me was this, roughly 4x more efficient to train than the other recent approaches. So that was really interesting, like how they managed. I still don't find, I didn't find their code also. This is from NVIDIA, I think. Oh yeah, okay. So I didn't find their code on Papers with Code yet. But yeah, that looked.
Yeah, in fact, one thing I've been wondering, talking of these back and forth, is what's the equivalent in NLP of the dynamic unit type of stuff? Because I haven't seen that kind of, the fact that what would be the equivalent thing of doing something like that?
But
and whether
in terms of what though, like what is the objective?
The objective being, dynamic unit, you pass forward from, the encoder decoder kind of structure.
Right.
You're passing words, if you will. And as I was just saying, it's like what at different levels of composition, you're trying to reconstrue what was originally there in your text, right?
Mm-hmm.
Because in the images, you're trying to reconstruct your original image. And
right.
That's why when you're doing segmentation, so by taking that kind of approach of trying to reconstruct your original text after you've broken it up and composed, would you get a better language model?
I mean, for me, like if you think of it that any seek-to-seek, basically, in a sense, if you're getting in words and you're spitting out words, it kind of is doing that, because you kind of go down the encoder path, go down like your embeddings,
right?
And then you kind of construct those back up, and you kind of get back words again. But yeah, I don't know if that's an exact parallel like with dynamic unit sort of a thing. But yeah, that's an interesting thought.
Okay, so I think we're 10 minutes past even 11:30. So next, thanks Raquel, thanks Steve for going through. I think that was very interesting. And next week, let's start with what you mentioned, Raquel, of the couple of tweaks and kind of discussing that somewhat. And then subsequently, once you're done, we can look at the HRNet, which is kind of ends our sequence of paper. And then if people are interested, maybe the following week, we can do what you suggested and kind of circle back on attention and other ideas of combinations of stuff.
Yeah, the thing I really like about attention is that everywhere where you can say like, oh, okay, this is worthwhile paying some concentration on this, they throw in this layer and they say like, okay, go ahead and figure out what you want to learn and then construct something back. And I just found that like a very recurring theme. And I did not know that there was an implementation there. So that's why I'm keen looking at that.
Yeah, no, that's a very good find. So yeah, if you can post a link to that, that'd be great. And thanks, Antonio, for sharing that HRNet video. I haven't looked at it, but we'll do so.
Thanks, Raquel, for the awesome presentation. And thanks to Steve also. Thanks, everyone.
Okay. So next week, we'll start with Raquel of just the couple of ideas, tweaks, as you said, and then we'll kind of go through the HRNet paper in the time left, and then we'll see whether we do one more on attention and circling the wagons back on attention. Maybe even because the unit was not recorded, Raquel, when you went through it, the dynamic unit and the attention and the ICNL and stuff. So maybe we use that as an opportunity to kind of quickly cycle back, starting from there and then diving into attention as well. Because unfortunately, it was one of those which went on Google and wasn't on the recording.
Right.
Yeah, I'm at the same point as Raquel. I just recently started learning about attention, and I just read the works on NLP. So I'm just recently trying to get into the research on attention for computer vision. And
if you guys have time, check out SqueezeNet also. Kind of has the similar concept. It's a nice starting point. If you look at the SqueezeNet architecture, I mean, it makes so much sense once you look at it. We can have like a quick 5-minute discussion if you guys want next time what SqueezeNet actually does.
Okay, sounds good.